There are two types of wave interference, constructive and destructive. In constructive interference, two similar waves come together to form a larger wave. Think 1 + 1 = 2. In destructive interference, two opposite waves come together and cancel each other out. Think 1 - 1 = 0. To make this more intuitive, imagine that you're on a trampoline. To jump higher, you perform constructive interference. You push up, and at the same time, the trampoline pushes you up. As a result, you jump higher. Now imagine that you want to stop bouncing. To do this, you perform destructive interference. The trampoline pushes up, but this time you absorb the shock. As a result, you stop bouncing. These same principles apply to sound. What if we could get rid of that? This experiment shows that speakers are capable of constructive and destructive interference. The speakers on the left are playing identical tones. The result is constructive interference. They work together to create a louder noise. The speakers on the right are playing opposite tones, demonstrating destructive interference. These two speakers are canceling each other out. My experiment showed a difference of 8 decibels, proving that speakers are capable of performing wave interference. You can try this at home by swapping the red and black wires on one of your speakers. Or you can play this video. Keep in mind that this demonstration only works with speakers, no headphones. The sound waves need to be able to hit each other before they reach your ears. Also keep in mind that noise cancellation works best at lower frequencies. Pay attention to the bass. Pretty cool, right? We found a way to make noise and destroy it. Very cool, but not very helpful. Why make noise just to destroy it? In order to make this phenomenon practical, we need a way to catch waves and invert them in real time. Luckily, we have that technology. Microphones catch sound waves in real time and convert them into an electric signal. We could send this signal to a computer, which will invert the wave. Next, that wave goes on to an amplifier, and finally the speaker. Just like that, you have the ability to destructively cancel sound waves in real time. We refer to this process as active noise cancellation. Let's see what this sort of system would sound like in our electric car. Wow, incredible. Active noise cancellation is most often used in headphones and high-end luxury cars. The best headphones are capable of blocking frequencies between 30 and 1000 Hz. High-end luxury cars are only capable of blocking frequencies between 30 and 500 Hz. We're now going to talk about why headphones are more effective at noise cancellation than cars are. You're probably familiar with water waves. Water is not easily compressible, so when pressure is applied, the displaced water moves along the surface, forming peaks and troughs. These surface waves are called transverse waves because the disturbance is perpendicular to the direction the wave travels. Sound waves move through air. Air can be compressed, meaning there is no reason for the wave to form a perpendicular motion. Sound waves move parallel to the direction of displacement. We call this a longitudinal wave. The key takeaway from this demonstration is that sound is more able to spread in all directions at once. Water waves move only along the surface of the water. Sound waves move in all directions, like an explosion. This adds a significant level of complexity to canceling noise in open spaces, like a car. If there is a speaker on the ceiling and a noise source coming from the wall, then the speaker will have to do much more math to calculate the amount of time needed for the canceling wave to intercept the source wave. This added distance also negatively impacts the response time of noise cancellation. By comparison, headphones sit directly over your ears. This decreases response time, allowing the speakers to cancel out higher frequency sounds. Up to this point, we've only modeled canceling one wave at a time. Close your eyes and try to identify how many sources of noise surround you. Each noise source adds an extra level of complexity. The more complex your environment is, the harder it will be to cancel noise. On the other end of the spectrum, it's very easy to cancel out consistent noises. In fact, we do it every day. 107 decibels. That's almost as loud as a Taylor Swift concert. You may notice that most cars are not this loud. These two cars have the same sized engine, yet the gray one is no louder than a toilet. Look underneath and you find your reason. The gray one has a big box connected to the tailpipes. The red car took their box and threw it away. As it turns out, mufflers do more than just muffle. They use destructive interference to eliminate sound waves entirely. As sound waves enter the chamber, they go to the back wall and bounce back. As it bounces back, the pressure wave is reversed. You can space these walls to cancel out a specific set of frequencies. Mufflers use multiple chambers as a way to cancel out a wide range of frequencies. Sound travels through this maze of chambers until it has been sculpted to the manufacturer's exact specifications. Most choose a soft rumble. Others choose something more exhilarating. Recently, some manufacturers have decided to ditch the exhaust note altogether. By now, you may have noticed that none of our demos have canceled all noise. As wave frequency increases, the wavelengths become smaller and more difficult to cancel. Modern technology isn't fast enough to cancel out these high-frequency waves, but high-frequency waves can be canceled. This is the first experiment used to develop the theory of wave interference. We're going to play an E on the first string and an E on the second string. Play them together and the noise gets louder. Constructive interference. Now, I'm going to bend the E note so that it's slightly out of tune. By itself, it produces a smooth sound. However, if we play this bended E at the same time as a regular E, we get a different result. This time, the sound is not smooth. You start to hear it cut in and out. By detuning one string, we've caused the waves to go slightly out of phase. When this happens, our waves rapidly swap between constructive and destructive interference. Thomas Young's next experiment would prove that water was capable of experiencing wave interference. 195 years later, this model would be used to explain rogue waves, a form of constructive interference. These two experiments alone would secure his place in the history books, but he had much greater plans. He set out to prove that light was a wave, and he succeeded. The double slit experiment. By shining a light through two separate slits, Young showed that light formed interference patterns similar to those found in the water interference experiment. This experiment proved that light was a wave, disproving Newton's corpuscular theory of light. 130 years later, the double slit experiment would be used to discover superposition, a theory so monumental and mysterious that it began the modern era of physics. Today we are capable of canceling out sound. Tomorrow we may be canceling light.